Hello everyone, this is allLogarithmsEqual, in a kind of continuation video of the Arbelos and Pappus chain lesson that I did and released about a week ago, or perhaps a few weeks ago. And so, as is already clear, probably, I was able to get better software and hardware for these kinds of lessons that I do. So thank you very much, for watching, and, hopefully this video will be of better quality than that which you're used to on this channel. And that is my hope, at least. I've actually gotten better software in the form of XSplit and hardware in terms of course, the webcam. But anyways, the point is, to the actual presentation. So here you should be able to see me actually on the lower right hand corner. Just give me one moment if you don't mind. Okay, I feel like I'm just getting the impression that this would be perhaps better if I had multiple monitors. But the point is, yeah, hopefully you can see me in the lower right, and over on the left and the main screen you can see this is the continuation of that lesson on the Arbelos and the Pappus chain. So without any further ado, we should move on. Well, I should move on. Okay, so basically what we'll be focusing on today is actually Proposition 5 from Archimedes Book of Lemmas. That same document to which I referred in the prequel video, as I guess what I'll call it, the prequel video. The Book of Lemmas by Archimedes, that set of 15 propositions that sort of serve as an extension, a very interesting geometrical extension to Euclid's Elements. So it's very interesting. And of course, the main theorem of today will state, and it will prove, that these two blue circles, which you can see on the right, or on the left, it's your left, is that those two blue circles are congruent to each other. And I'm going to use a couple of different sources to, study the proof of this and to show you the proof of this. One of which is the website cutthenot.org, which has this bit of information right here. Basically, it's saying, let AB be the diameter of a semicircle, C on any point AB, C any point on AB, and CD perpendicular to it. And let semicircles be described within the first semicircle and having AC, CB as diameters. So you can see the diagram there, the two smaller semicircles nested within the larger semicircle, which that's just a definition, constructing the Arbelos figure. And then it says, if two circles be drawn, touching CD on different sides, and each touching two of the semicircles, the circles so drawn will be equal. So it's stating the same thing. Those two circles that are tangent to two of the semicircles, and of course that altitude, I'm going to call it an altitude, which in this diagram is CD, segment CD. Those two circles are congruent to each other. So moving on, in order to really accurately study the proof of this, it might help to actually go back to, this is a PDF version, this is a browser, a PDF version of Archimedes Book of Lemmas. And so starting from the beginning, this is just sort of constructing the basics of it. Constructing, what we see in this diagram right here. And so it says, let one of the circles touch CD at E. So it's describing this circle on the left, is what I'll call it. It's touching the altitude CD at the point E. And the semicircle on AB in F. So the point F on the largest semicircle is another point on that left circle. And the semicircle on AC in G. So semicircle AC, intersects this left circle at point G. Alright, so this is just setting up the different points on the diagram. Draw the diameter EH of the circle. So EH which will accordingly be perpendicular to CD and therefore parallel to AB. So it's sort of like, again, just building upon the theorems of Euclid, where basically we know that there is a diameter. We can actually draw, since the circle's tangent to this altitude CD, we can actually construct one line segment through the point E that is perpendicular to CD, and that will be a diameter of the circle. So that's what HE is. That's just stating that we can construct that. It's a diameter of the circle, and since the circle's tangent to CD, we know that EH must be perpendicular to CD, and then of course it's sort of like a, almost like it's just a property of segments being perpendicular or parallel. So if two segments are perpendicular to the same altitude, in this case CD, then they are parallel to each other. So HE is obviously parallel to segment AB. Then it says join FH, HA, and FE, EB. So that's just sort of constructing these lines, or we're about to prove in a moment that they are straight lines. But for the moment, we just know that they're segments, sort of segments that are separate from each other, although they share the point H. They share the endpoint H. So AH, FH, BE, and FE. So it's forming these two segments, which hopefully you can see. Hopefully you can see my cursor over there. But it's these two segments is essentially what we're drawing in. And it's stating by proposition 1, FHA, FEB, so FHA and FEB are both straight lines, since EH and AB are parallel. So what it's basically saying, and you can also see this here. Basically what I'm showing, what Archimedes is showing is that proposition 1, based on proposition 1, we know that basically, since we have these two circles that are tangent to each other in a single point, so if you consider the first circle, the left circle, being tangent to the largest semicircle at point F, then we know by proposition 1, since HE and AB are parallel to each other, that means what we actually have are two parallel diameters. Now, parallel diameters is actually very special to Archimedes' Book of Lemmas, because it's proposition 1. Proposition 1 applies when we have parallel diameters of circles that are tangent at a point, which is what we see right here. So that's basically just proving that F, H, and A all lie on a straight line. So they're collinear. And it also applies to F, E, and B. So F, E, and B, that also forms a straight line. It's pretty obvious based on the diagram we see right there, but I just wanted to show you, because that's an application of proposition 1 from the Book of Lemmas. It also says, for the same reason, AGE and CGH are straight lines. So this is what I was getting into a bit prematurely, I suppose. So AGE, you can see, at the point G, that's really our special point in this case, because that's the point of tangency between the left circle, the complete circle, that left complete circle, and the semicircle, the kind of small, well, it's not the smallest semicircle, but it's the semicircle on the left. So that point G, obviously, is the point of tangency. And so, again, because we know that HE is parallel to AB, we can also say that there are straight lines through the point of tangency, basically. That connect the endpoints of the diameters, is basically what we're saying. So, as a result, you know, AC is a diameter, HE is a diameter. So the straight lines that are applicable in that case are AGE, that's a straight line, and CGH. So anyways, I don't want to waste any more time on that because there's more interesting stuff in this proof. Let AF produced meet CD and D. Okay, so AF, we've already defined the point F being the tangent point between a left circle way over there, and the semicircle, you know, A being part of one of the largest, you know, the large diameter with which we started. A is one of those endpoints. So it's just saying if we extend the line through A and F, you know, extend that forward and upward from our perspective. It's upward until you reach that point D. And let AE produced meet the outer semicircle in I. So, again, we're just saying draw the line AE and extend it upward and to the right. And where that line meets the outer semicircle, the largest semicircle, that we'll define as I, point I, okay? And then we can join the segments BI and ID. So again, toward the right, we can join the segments BI and ID on sort of the second, or the right section of the entire diagram. And now it makes use of some very interesting things. It says, since the angles AFB and ACD are right. So let's unpack that for a little bit. AFB is, so angle AFB is a right angle by Thales' theorem, which we described before. What we see is basically, and you sort of have to, in some sense, train your mind to look for these things sometimes, and make sure you can see the different sort of subsections and, yeah, subsections of a diagram, and see it in different ways. But obviously, here we have angle AFB, you know, the triangle. We can actually see the triangle AFB. Focus on that triangle and you'll notice that basically it is a triangle inscribed within a circle. That circle being the largest semicircle. In which one of the sides of the triangle, AB, is of course the diameter. It was just originally defined to be the diameter of the circle, or semicircle. So as a result, by Thales' theorem, we know it's a right triangle, and we know angle AFB is right. Now, moving forward, we also know ACD is right, just by definition, because, of course, CD, that segment, that altitude, is, by definition, perpendicular to AB. So that's a simpler explanation, I suppose. But as a result, it says the straight lines AD and AB are such that the perpendiculars on each from the extremity of the other meet in the point E. Right, now this is where it gets a little bit more complicated, but it's just saying basically that the segments AD and AB, we can consider, in fact, a new triangle, a different triangle. This time let's consider triangle ADB. So as for that triangle, we know for certain, because those angles are right, AFB and ACD, well, those triangles are in fact sub-triangles in some sense, that are nested inside this large, you know, main triangle that is ADB. And so, what we also know is that basically CD is one of the altitudes. That's why I've been calling it an altitude this whole time. It is in fact an altitude of that largest triangle, ADB, because it's a line through one of the vertices, D, and it's perpendicular to the opposite side. So that's just the definition of an altitude, if you don't already know. And so we can also say the same thing, interestingly enough, for BF. So segment BF is an altitude of that same triangle. It's another altitude, right? It goes through the vertex B, the closest one there is to my face. Going through, or rather, it's an altitude because it goes through to the other side of that same triangle, and it meets it at F. Point F is the important thing. And we know that that's the right angle, so it's perpendicular, and by definition, it's an altitude. So if two of the altitudes meet at that point, we know by a property of triangles, it's basically saying that, and this is, I got this from a different source, by the way, but this is describing the orthocenter. So it's a theorem in Euclidean geometry that, of course, all the altitudes of a triangle meet at a single point, and that's the orthocenter. So if we have two altitudes that meet at a single point, we know the third altitude must also meet at that point. This is actually rather interesting how we can prove this, however obvious it might be at first glance. But basically what we're seeing is that the segment, what we've proved is that the segment AE, which is of course the segment that is going from that vertex A all the way over there to the left, the segment through that point that also meets at E must, and we sort of indirectly proved it, but it must be the other altitude of that large triangle ADB. Therefore, what it's basically saying is that AE, the segment, is perpendicular to the line that joins B to D. So that's the text we see, right above the diagram. That's just all that that's trying to explain. And we also know, a very interesting perspective on this, is that we can see actually yet another subtriangle, and that is AIB. If we consider that subtriangle, we know, we constructed a while ago, the point I being on the outer semicircle. And so we know that that is a triangle, another triangle, where one of the sides is, of course, AB. So by Thales' theorem, we again know that AE, or rather, we know that, angle AIB is a right angle. And so by deduction, AE must be perpendicular to BI. And so basically what we're saying is that that is the same line segment, basically. It says, by the properties of triangles, AE is perpendicular to the line joining B to D. Well, what we're spending all this time doing is proving that BID is a straight line. So I also lies on that line, on that segment, or side of the triangle, however you want to think of it, to which AE is perpendicular. And now it uses a lot of similar triangle phenomenon. This is what we're getting into. This is probably the most vital or most important part of this lesson, really, or of this proof, in my opinion. So basically, since the angles at G and I are right, I know that that's somewhat vague how it says the angles at G, angles at I, but it's done deliberately, if you think about it, because the only, in this diagram at least, which we're seeing, the only angles that are drawn through the point G involve the segments CH and AE. So, in other words, I guess my point is, no matter which angles you choose, those four angles are all right angles, is basically all that it's saying, of the segments that are actually explicitly drawn in this diagram. So, whether we're talking about angle AGC, or HGE or CGE or AGH. All four of those are right angles. And the same can be said for point I. You know, in that case, there are two right angles, you know, that we can identify there, being AIB and AID. But again, just resulting from Thales' theorem, because we have perpendicular lines, they meet at right angles, by definition. And it's also saying that CH is parallel to BD. So let's unpack that for a moment, if we haven't already. CH, right here, is parallel to BD. So let's take a moment. Right, basically what we're saying is that by similar logic, since CH is perpendicular to AG, and of course AGI is a straight line, so we could equivalently say CH, that segment, is perpendicular to AI, and BD, or BI, whichever one, you know, is perpendicular to AI. We basically know, you know, we have two line segments that are perpendicular to the same line, so by definition they must be parallel. Well, not by definition, there's a theorem for that, I think, but the point is, CH is now, we know now that segment CH is parallel to segment BD. And so from here we can use sort of a chain of triangle similarity ratios, which turn out to be very interesting. We have, therefore, AB to BC. So the ratio of these lengths that are on the diameter of the largest semicircle, AB to BC, is equal to the ratio AD to DH. So this is, again, resulting from triangle similarity. So what we see, and specifically this particular triangle that we're looking at in this case, is triangle AHC and ADB. Because, of course, we have some shared segments there, and a set of parallel lines. So, in other words, again, a triangle nested within another triangle. But basically we know that AB, and you know, I'm beginning to think that maybe it would be better if I had some sort of a sketch. Like if I could use a tablet or something for this. Or not necessarily a tablet, but something where I could, you know, where you could see my writing. But anyways, the point is, so we know that the ratios AB to BC equal, and AD to DH must be equal. And also, using a different set of parallel triangles, similar triangles, we know basically we can focus on the triangles HDE and ADC. So using HDE and ADC, again, we have a sort of set of nested triangles right there. What we can say is that just focusing on the ratio AD to DH on that one side of the triangle, on the leftmost straight line, that's upward sloping, so AD to DH, we know by a different pair of similar triangles that must be equal to AC to HE. Because again, we're using this this ratio. So AD is a side in the larger triangle, ADC. As is AC. And DH is a side of a smaller, relatively smaller triangle, as is HE. So that's, we're just drawing another similarity statement there. And then after that, we can actually say, by cross multiplication, we can actually say that AB times HE must be equal to AC times CB. So this is this statement right here. Hopefully you can see that. Hopefully you can see this cursor. Otherwise, that would be a little bit sad that I'm just, like, pointing on this, you know, on the screen over there. I'm trying to highlight something. Or not exactly highlight, but I hope you can see my cursor, because that's the important statement where we are. And it says, in like manner, if D is the diameter of the other circle, so just bear in mind for a moment that we know that HE is, of course, the diameter of the left circle. That's what we've been focusing on this whole time. The leftmost circle, complete circle, I mean, not just semicircle. That one we know to be HE. That's the one we've been dealing with this whole time. And it says, if D is the diameter of the other circle, so the one closer to me, closer to the ALE sign above my head, that right circle, let's suppose it has diameter D, and it's saying we can prove, similarly, that AC times CB equals AB times D. Therefore, D equals HE, and the circles are, of course, congruent. So, thank you very much for watching. I hope that was enjoyable. I hope that was informative. You know, let me know if you have any questions. And, other than that, I think I will be able to leave you. Yeah, this video, I think, is large enough as it is, and I'll probably need to do some editing. But, by any rate, you know, I hope you enjoyed that. I hope that was informative. And, again, if you have any questions or comments, let me know. Yeah, thanks.